We have Tristan Buckmaster here from downtown from NYU speaking to us about singularities in fluids, self-similar analysis, computer-assisted proofs, and neural networks.
Thank you very much for the invitation. I just want, so in this talk, it's going to be a different sort of talk. It's not, I want to talk about sort of a general program where we're using machine learning techniques and using some sort of, it's a combination of sort of pure mathematics and computer assisted proof. And so it has sort of three different sort of flavors, which I'll talk about. And so just to give the concept of what we're trying to do. So I'm interested in self-similar singularities. And so this is a simple model, and I'll write the equation next. So this is the Burger's equation, which is probably the simplest evolutionary nonlinear PDE. When you study undergraduate PDE, you know that a singularity happens in finite time, which is a shock forms. And so this is the formation of shock where the gradient here is going to infinity. So if you look at the evolution of the solution to the PDE, it's given by this blue curve in the first picture. And now if you draw this red box and you zoom this red box in, and then this red box is the outline of this black box here. So you zoom things out. Then what you see is this blue curve is the same blue curve as there, but it's been stretched in a very particular way. And you go from a problem where something is becoming singular, in this case the gradient is going to infinity, to something which becomes a stability phenomena, where it's actually converging to something nice. So in this case, the orange curve is what it's converging to. So this is self-similar analysis. So you take something, so you could imagine even like numerically, if you're trying to solve something like this, if you're trying to do a numerical simulation, something where things become infinite, become difficult for a computer to solve, but things where everything becomes stable and nice is something where it becomes more tangible. So this is, to be more explicit, what this toy problem is. So this is just the Burger's equation, and you learn in undergraduate PDE that by following characteristics you solve the Burger's equation. Now I want to introduce what this red box is. So you make the sort of ansatz that the solution has this self-similar structure, which is given in the first equation here. So what you see is that the solution itself depends in space and time, but with this capital U, it only depends in space. And this capital U will be this stationary orange curve given in this picture here. And so what happens is that you translate this PDE into an ODE, which you can solve. And this is the corresponding ODE. So it becomes like a nonlinear eigenvalue problem. So you have to solve for both lambda and for U simultaneously. And then solutions to this represent solutions to self-similar profiles to these fluid equations. So that's the basic setup. And so here's the equations, and you can just rearrange the equations and you get an implicit solution to this equation. And if you just do a bit of counting, if you just look at this implicit equation, you realize that the solutions can only be smooth. I should point out also, why do we care about singularities, and why do we care about like smooth solutions to these equations? So this is all kind of related to the general questions related to the sort of the Millennium Prize type problems. I'm not going to talk about the Millennium Prize at all in this lecture, but the basic idea is that you have some sort of PDE, so a fluid PDE, and you have, you have a fluid PDE where you want to construct some sort of initial state where if you flow the equations forward in time, eventually there's a singularity. And you want that the initial conditions are smooth. So for the self-similar profile to be smooth, you see from the implicit equation that you must have this 1 plus 1 over lambda. So lambda is this self-similar exponent, must be an integer. And then for it to be globally defined, you need that this integer is odd. And then you are left with certain candidate self-similar exponents. This lambda is 1 over 2i plus 2. And each one is a solution. The first one, I equals 0, you can actually explicitly write down what the formula is. And this corresponds to this seems like a toy problem, like it's a Burger's equation, but actually this solution you see all the time in nature. So anytime there's a shock wave, this is before the shock wave occurs, this is what the fluid will look like before the shock wave occurs. Even for much more complicated equations, which have many more terms, at the sort of limit, you end up with a sort of Burger's-like solution. Something I will try to... so as I said, there's many different actual solutions. There's corresponding to all the different lambdas. There's one for every I. So there's a discrete family of self-similar profiles to this equation. And I want to define what it means to be a stable self-similar singularity. So if we write solution to the Burger's equation as the rescaled self-similar profile plus some perturbation, then we end up having some equation for the perturbation. And I'm going to do something else where I'm going to change time. So if the time of the singularity is at time 1, I'm just going to remap this until the time of singularity is at time, in this S variable is at time infinity. And you end up with this sort of equation where you have, this is the linearization of the equation, self-similar equation around the profile, and then you have some nonlinear terms. So what it means to be a stable solution to this equation is that this linearization, this linear operator, has all its eigenvalues. The only positive eigenvalues it has, or only non-negative eigenvalues it has, are generated by the symmetries of the equations themselves. So, for example, if you imagine you take the same initial data, but you translated it. A singularity will still occur. It's just that the window that you're zooming into will be the wrong window. Okay, that will generate an instability. Or if you make the amplitude a little bit bigger, or you wait a little bit longer, all these things correspond to symmetries of the equation. So modulo these symmetries, what it means is a solution to be stable is that none of the eigenvalues generated by the symmetries have positive real part. And so, and what you should think of these stable singularities as, like, if I do nothing, the evolution of the equation will naturally lead to a singularity. Whereas an unstable self-similar singularity, if I just perturb it, any slight tiny perturbation, the singularity will not occur. Okay, and I'll explain in the future. So when we're interested in problems like, let's say, the Millennium Prize or so forth, it's quite possible that we're looking for unstable solutions, not stable solutions. I mean, if it was a singularity occurred for the Navier-Stokes equation and it was stable, we would have probably already seen it. You know, people have been working on this for quite a while. People doing numerical experiments, etc. if there was a stable singularity, it would have already been seen. And we've seen for a lot of other equations that you can overcome these things like viscosity and so forth, which I'll explain in a later slide, by considering unstable solutions. So one effect this has in the Navier-Stokes problem, one thing people often ask, if there's a singularity to the Navier-Stokes equation, does that mean the whole equations are useless? Of course, that's not true. But it also means that if the singularity does exist, then it's quite possible that you would actually never see it. Like, there's zero probability that this solution would actually occur given any initial data. Okay. So this was a video I took when I was back home in Australia, and I happened to see a singularity in the ocean and a mathematician writing down a proof. So I took a video of that. Now, okay, so one question is, how do we find these self-similar profiles? So in this case, I can actually just write it. It's a nice, easy formula. But in most cases, it won't be some simple formula. So in 2014, Lu and Hao presented a scenario for a singularity for the Euler equations, which is just like the Navier-Stokes but without viscosity, in the case that there's a cylindrical boundary. And they provide some numerical evidence that shows that a singularity occurs, and this numerical evidence suggested some sort of asymptotic self-similar scaling. And a rigorous proof was recently given by Chen and Hao in 2 papers in 22 and 23. Okay, so the basic setup is the first observation is that the world is flat. So when you zoom in on a cylinder, it becomes flat. So this one thing that you should take from this is that. So I should say that the idea of looking for self-similar singularities isn't something that's happened in the last 10 years. It's people have been studying this in PDs for a very long time. But it was only sort of recently that people thought finding self-similar singularities is possible in the context of fluids. And one of the reasons why is there was a lot of evidence, there was proofs that singularities could not occur if you had some sort of you had some additional assumptions on the profile, such as finite energy and so forth. And the upshot is that the additional assumptions that people made were not quite relevant for fluids, because the self-similar profiles only describe what the singularity looks like at the point of the singularity and at the time of the singularity, and they have nothing to do with the solution away. So going back to this problem, the self-similar profile, you have to zoom in on the boundary where the singularity occurs, and as you zoom in, the cylinder becomes flat. So we'll assume axisymmetry, so you end up working on a half plane. And it turns out that the equations you get, you end up getting the self-similar equations you get relate to a self-similar solution to a different equation called the Boussinesq equation, which is on the half plane. And essentially, you can show by perturbative arguments that if you have a self-similar solution to this other equation, the Boussinesq equation, then you get a self-similar solution to the Euler equation plus some decaying terms that you can deal with. And this is what was used to prove law in this case. Now, Okay, so again, you end up with this problem where you have to find these vector fields, and you have to find some lambda. And the first step in this kind of proof is you have to find the self-similar profile. And you can't do this by hand. You have to do it to use some sort of numerical method. And so we came up with this. So this came out with a. So when I was in Princeton, I had to sign off on an undergraduate research project by Charlie Cohen-Breen, who was working on the viscosity of ice sheets in Antarctica. And I thought, this is certainly very relevant to my research. And so what they were doing is they were using these pins, which is a super simple concept. So everyone's aware of, like, you write. So the idea is to find these vector fields, in this case, omega and u. So omega, and how you find, and you want to have some sort of optimization problem which will solve these equations along with this self-similar parameter lambda at the same time. And so the first thing you could think of is that everyone, you can represent these solutions by, let's say, a linear basis, like a Fourier series. And so instead of doing that, what we do is we represent the solutions by a more complicated basis, which is a neural network. So all you should think of this neural network is representation of the solution, where it's just a sequence of it's linear sums and compositions, and applications of nonlinear activation functions and compositions. And for that, it gives you you should think of this as just a very complicated way of representing a function. Okay, there's a discrete number of coefficients, just like you have a discrete number of coefficients for a Fourier series. And the idea is that you'll be optimizing these coefficients in order to find a solution to the equation. So you take your random function and then you just put it into the equation, and then you differentiate this, the resulting, so then you'll get some error, and then you differentiate this with respect to all the coefficients representing the function. And this provides your, it's a gradient descent way of optimizing these coefficients in order to actually solve the equation. So this is the basic idea. So it's not, it's not a super complicated setup. In fact, it's pretty, the whole setup is pretty sort of traditional numerics in a sense. The only sort of slight twist is that you have this complicated representation of the functions. Okay, so and now before I just present some of the results, so the first result we had was that we found this, we found the self-similar profile, which was suggested by the work of Liu and Hao. But before I talk about some of the more recent results, I also want to talk about why we're interested in so-called unstable solutions, which are particularly hard to find. So this is just a different equation. It's called the Cordoba-Fonta loss equation, and it's a sort of toy model, a 1D toy model that you can play with the interface between Euler and Navier-Stokes. Euler being where you have no viscosity, and Navier-Stokes where you have viscosity. So you add this additional red term, and you have this parameter alpha where you can sort of make the viscosity stronger or weaker. Now you look for a solution to the CCF equation where with no viscosity. And so this is, you end up having, you do the same procedure as before, and you rewrite the equation in self-similar coordinates, and you get all these terms, and then you get this additional term which comes from the viscosity. And one thing to keep in mind, one thing to point out, is that whether this term decays or grows depends on the self-similar parameter lambda. Now, it's an open, so we know singularities occur for alpha between 0 and 1/2, and we know that no singularities can occur for alpha between, for alpha greater than 1. And then the remaining questions for this simple model is what happens between 1/2 and 1. Now, by doing a quick calculation to see when this exponent is negative, i.e. we can ignore viscosity, one sees that you need that lambda is less than 1 on alpha minus 1. So in order to address the open range between 1/2 and 1, you need lambda is less than 1. And okay, so now this is, I'll complete this story with the CCF. So the stable solution, which is a stable blow up, the implicit problem has lambda greater than 1. So if you want to address, the unstable problems, you have to consider these, if you want to address the open range, then you have to consider these unstable solutions. And you can imagine that there's an infinite number of unstable solutions. And so this is a potential strategy of how you get rid of viscosity. Okay, so this is, and this is why we were interested in unstable solutions to begin with. And you can imagine from traditional numerics that it's very hard to find these unstable solutions. You cannot just evolve, the traditional way that these self-similar profiles were found were by evolving things in time. And that's exactly what Lua and Howe did. They evolved things in time. But if it's unstable, you just can't do that. It just doesn't converge to anything useful. So our method kind of gets rid of that in the fact that we look for the profile directly and there's no time evolution at all. And this is what we got. So this is not the first paper. This is the second paper with so Yonji Wang was the first, who was my postdoc. Gonzalo Carlavora, Javi Gomez Serrano, and Qingyao Lei, who's at Stanford, and then also with DeepMind. So we went. So our first paper we had these blue solutions here. And then in this follow-up paper, we suddenly found all these other solutions, which were quite difficult to find. And the main difficulty in finding them is that as they get more and more unstable, you end up having these huge gradients, which are just very hard to deal with. And then, yes?
So, you're numerically using the neural net to construct some approximate.
Yes, that's right. That's right. How much time do I have? Okay, so I'll try to get to that bit of the question. So yeah, and then in a later paper, also with Leger, Yonji and Qingyao Lei, we also, we went further and we were able to sort of find the fourth unstable for this other equation IPM. And all the errors, this graph can be confusing. This is not the solution. This is the error. Okay, and the important thing is that the error is at the level of machine precision that you get from round-off error. Okay, so at this point, we're kind of constrained by the fact that NVIDIA doesn't want to give me great GPUs with quadruple precision. apparently that's not, I'm not a big enough market. So, okay, so so that was just creating a numerical. It's not a proof. So to get a proof, I need a robot that can write on the paper even before writing on the paper. So the basic idea is that you want to take this numerical solution and convert it into actual proof. So you marry numerics with rigorous mathematics, and this is kind of a general program that works in many PDE. So one big instruction we have in PDE of proving some big theorems is just simply we can't write down these particular solutions by hand, right? And we can't characterize them with pen and paper. So there's some way to link some numerics with actual rigor, then we're able to sort of prove things that would just be impossible to do with pen and paper. So the first step is to identify your self-similar profile with some numerics, and then you have to rigorously bound all the errors, and this is with interval arithmetic. And I won't go on to the details of rigorous interval arithmetic, but I do want to advocate for it, because when we talk about computer-assisted proof, it's normally we talk about lean, when we talk about formalization. This is a different type of computer-assisted proof, which I think is very powerful and is sort of underappreciated. So we rigorously bound all the errors. So actually, we take this neural network representation and we re-represent it. We throw it away and we represent it in a linear basis. And then we bound all the errors and also the derivatives of the errors. And then you need some explicit bound. So you need some explicit fact that the linearization, its non-compact part is dissipative. And so that means that it's dissipative modulo some finite rank operator. And this is kind of the key estimate you have. And then that plus 300 pages of math, you can get a proof. So you need to split things into stable, unstable manifold, and that's kind of, And so this is just some pictures of the spectrum, but just having the spectrum is not enough. You still need to bound like transient growth. And so that's a key idea. And so this is this is just sort of, this slide, you learn this in your undergraduate ODE course of how to sort of, it's a PD, but you learn how to decompose things into stable, unstable parts. And the main observation is if you have that estimate before, then if you take that linear operator and you subtract this finite rank operator, you can formally, you can define its inverse if you have this distributivity estimate. Okay, and then anyway, I won't go into these details, but the main idea is that once you have this estimate with a lot of effort, you can turn it into a proof. Okay, and why do you expect that you get this? This sign. Why do you get? It's actually from a kind of a simple. There's a simple reason. So when you look at this linear operator, you see that there's this term like minus 3 on 2 y in the case of the Burgers equation. Times the derivative of u. And this term arises just from the change of coordinates. The change to the self-similar coordinates. When you differentiate this enough, you end up with a positive damping term. And this positive damping term is what creates the sign you get for the non-compact part of the operator. And I probably have gone over time. Anyway, this is sort of interval arithmetic. where you just replace your traditional floating point arithmetic with intervals, where you, instead of just adding two numbers together, you add two intervals together, and the result is another interval which contains the sum of the two intervals. And that's the basic property of interval arithmetic. And with this very simple tool and a ton of tedious calculations and tedious computations, you can take traditional numerical analysis and actually make it rigorous. And so I'll leave it there.